Imagine a world where the rules of physics seem to bend and defy common sense. A recent experiment conducted by physicists has uncovered a phenomenon that does just that, challenging what we think we know about how particles behave when energy is continuously applied. But here's where it gets controversial. Could this discovery change the way we approach quantum technology? In our day-to-day experiences, we're familiar with the idea that adding energy to a system increases its temperature. For instance, rubbing your hands together generates warmth, and hammering a piece of metal will eventually make it hot. These observations align with our intuitive understanding that applying force or movement to any system, whether through stirring, pressing, or striking, typically results in a temperature increase. This principle extends to the microscopic realm of quantum mechanics, where we generally expect that continuously exciting a many-particle system, particularly one with strong interactions between particles, would lead to an increase in energy and, consequently, a rise in temperature. However, recent research from the University of Innsbruck suggests that this isn't always the case, especially at the quantum level. A team led by Hans-Christoph Nagerl from the Department of Experimental Physics at the University of Innsbruck has observed a fascinating phenomenon known as Many-Body Dynamical Localization, MBDL. Their findings, published in the prestigious journal Science, reveal a quantum gas that resists heating despite continuous external perturbations. The researchers created a one-dimensional quantum fluid composed of strongly interacting atoms, cooled to just a few billionths of a degree above absolute zero. To study the effects of continuous energy input, they subjected the atoms to a rapidly and periodically flashing lattice potential, akin to a series of quick, repetitive kicks. Under normal circumstances, one might expect the atoms to absorb energy over time, much like how repeated jumps on a trampoline would cause the surface to oscillate more and more. However, the team observed a surprising outcome. After an initial phase of energy absorption, the atoms' momentum distribution stabilized, and the system's kinetic energy reached a plateau. Despite the continuous kicking and strong interatomic interactions, the system ceased to absorb additional energy. This phenomenon, known as Many-Body Dynamical Localization, is a testament to the unique properties of quantum mechanics. In this state, quantum coherence and many-body entanglement prevent the system from reaching thermal equilibrium and exhibiting diffusive behavior, even when subjected to sustained external forces, explains Hans-Christoph Nagerl. The momentum distribution essentially freezes, maintaining its initial structure. Lead author Yanliang Guo admits that the results were unexpected. We initially anticipated that the atoms would scatter in all directions. Instead, they displayed an astonishingly ordered behavior. Lei Ying, a theoretical collaborator from Zhejiang University in Hangzhou, China, emphasizes the significance of the findings. This is contrary to our classical expectations. The fact that many-body coherence can halt energy absorption in a strongly driven and strongly interacting system highlights the profound stability inherent in quantum mechanics. Ying also points out the practical challenges of simulating such a system on a classical computer, underscoring the importance of experimental verification. That's why experiments are crucial. They complement our theoretical models and provide insights that simulations alone cannot offer. To further investigate the robustness of the MBDL phenomenon, the researchers introduced random variations into the driving sequence. Surprisingly, even a small amount of disorder was sufficient to disrupt the localization effect, leading to a smeared-out momentum distribution, a sharp increase in kinetic energy, and continuous energy absorption. This test underscores the critical role of quantum coherence in preventing thermalization in driven many-body systems, notes Hans-Christoph Nagerl. The implications of these findings extend beyond fundamental physics. Understanding how quantum systems can avoid thermalization is a crucial step in developing more advanced quantum technologies, such as quantum simulators and computers, where uncontrolled heating and decoherence pose significant challenges. This experiment offers a precise and highly tunable method for exploring how quantum systems can resist the onset of chaos, says Guo. The results not only open a new window into the physics of driven quantum matter, but also challenge long-standing assumptions about the behavior of quantum systems. What do you think? Could this discovery pave the way for breakthroughs in quantum technology, or are there deeper, more fundamental questions that need to be addressed first?